Good morning, everyone. Good afternoon, good evening, depending on where you're joining us from. It's morning here in California. My name is Nathan, and I'm a trainer here at Briggs Stratton Energy Solutions, and I'm joined by my colleague, Daniel Moyer. Morning, Daniel.
Good morning, Nathan. Hello, everyone.
So we've got people coming in here, and I'm going to allow those numbers to keep trickling up. But what we're going to be getting into today is a NABCEP certified training on why the battery management system matters and understanding the different functions of the PHI, AmpliPHI, and SimpliPhi BMS systems. So we'll get started in just a few minutes. As I mentioned, this is a NABCEP certified training. So if you're looking for those continuing education credits, please send us an email with your name as it is registered with NABCEP so that we can get it right on your certificate. And we will email you a certificate for attending today's NABCEP accredited training. Our email address will appear at the end. Please do stay through the entire presentation. You have 1.5 hours of credit for today's training. Also, if you have questions, we aren't able to unmute you, but if you can go ahead and use the Q&A section that should appear on your Zoom menu somewhere on your screen. Daniel will be able to answer some of these questions in real time. And Daniel, feel free to interrupt me if there are some questions that you think I should address during the webinar for everyone.
Absolutely.
So at Briggs & Stratton, we are trying to make energy simple. And we are launching and shipping our new SimpliPhi ESS. And we might mention that a few times during this presentation. You can see a marketing rendering of this system on the wall here. I've got a more realistic version of what an install looks like on the screen behind me. And so you can look at my picture there, see what that looks like. But this training is all about our BMS and our batteries. So we won't be spending a lot of time talking about the SimpliPhi ESS system, but we have upcoming trainings that do include that. And so if you're looking to learn more about the SimpliPhi ESS, look at our training calendar. We'll have a training coming up on August 31st on the SimpliPhi ESS. So Briggs & Stratton purchased SimpliPhi Power 2 years ago now. And Briggs & Stratton offers a long history, 115-year history of research and development. Well known in the engine business and also for their electric lawnmowers. You may not know this, but they produced a hybrid car back in the 70s. Daniel had brought that to my attention before. And SimpliPhi Power now has 13 years of experience developing, manufacturing, improving LFP batteries, which is the way the industry is going as in terms of the longest lasting best battery for home energy storage. It's a little bit heavier of a chemistry, as we'll talk about briefly, but it's really the best battery that's currently on the market for home energy storage. And together we are now offering a complete integrated energy solutions division. And we have comprehensive products that range from generators to inverters to complete backup systems, and we have training surrounding those. What's driving the market here? We're not going to talk a lot about this. We present this slide in each of our trainings, but just to highlight a couple of things, a lot of people are working from home now and want reliable access to power. We have infrastructure that needs investment. We have some failing infrastructure throughout the country, and often we're experiencing power outages. These outages are actually growing, and that is helping to drive the solar and battery market growth. Climate-related disasters, of course, are supposed to be on the rise due to climate change. These disasters result in outages, and having battery backup can provide continuous access to power. Of course, we cannot forget about everything is going electric right now. Probably the most common car in my area here in California is the Tesla Model 3, followed closely by the Tesla Model Y. More and more companies are releasing battery-powered cars, and this adoption to electric from lawnmowers, weed eaters, electric cars, is really helping to push the battery market forward. And also the growth of clean energy and those wanting to have clean and renewable energy is on the rise. And we see all of these things contributing to driving a very healthy growing battery market, which is expected to hit 6.6 billion by 2027. That's just 4 years away. And so there's a lot of growth there. The overall end use applications of these batteries allow many different advancements in terms of having control over your home's access to renewable energy, backup power, off-grid energy, etc. And so we're going to jump into those. So if you are an installer and you're here now, really is the time to get into solar as well as battery backup solutions. The energy storage market, only about 11% of solar owners have batteries right now. That's expected to grow to 33%. So 1 out of 3 solar installations is expected to have batteries. And over the next 5 years, it should increase this market by 40%. So what are the advantages of having battery storage over just solar, right? Having backup power, having the ability to use that energy even when the grid goes down. We can't say this for all solar installs, right? Many solar installations do not produce power if the grid goes down. Of course, there's this option of cycling your batteries, charging them up when energy is cheap or when energy is free when you're getting it from solar, discharging it to reduce higher rates, higher electric rates in the evening, etc. Storage and renewables offer this ability to save that energy during the day and discharge at nighttime when you need it. Of course, the off-grid market, you don't have access to grid, and so you can have power with storage in off-grid markets. And we can even optimize generators. So if you are in an off-grid situation and are looking to run your generator a little bit less, use less fuel, run it at the peak efficiencies, you can do so. If you have batteries, you can run your generator for a short time, charge up those batteries, and then discharge those batteries until they need charged again. And so there are a lot of reasons to have storage. We're going to talk about how that actually functions and how the battery management system plays a big role in healthy functioning systems. Why would you choose Briggs Stratton Energy Solutions? We know you have a lot of choices when it comes to batteries. First, I will say that we use the best battery chemistry that there is out there. We use LFP battery chemistry. That's lithium ferrophosphate. It doesn't include cobalt, makes for easier recycling of the batteries. No toxic heavy metals that are there. Additionally, we use the best cells and the longest lasting cells. So we're not making these batteries from cheaper cells. We're making our batteries from cylindrical cells. This allows us to offer the longest warranty in the business. Unlimited number of cycles, 15-year warranty on our AmpliPHI and SimpliPhi batteries. Expected 70% of their original capacity retained after 15 years. This is a great warranty on our batteries, probably the best warranty out there. And it's backed by a company that's going to be around, right? Briggs & Stratton's been around for 115 years. We can back up a 15-year warranty. Whether or not you trust another company that's offering a 10-year warranty to be around after 10 years when it's only a 5-year-old company, that's another question, right? So we're offering a very strong warranty here.
And one thing I would add to that, Nathan, is that there's no throughput clause as well. Unlimited cycles, unlimited throughput, 15 years.
Flat warranty, right? Great, Daniel, thank you. Yeah, so we're really standing behind our product because we're making the best battery on the market, right? We're using the best chemistry, we're using the best cells, and we're, as I'm going to explain, using a very high-end BMS that we've developed here in California. So we've got batteries in 45 countries. We have distributors around the world selling these batteries, over 300 plus megawatt hours installed since 2010. We've got many of our batteries out there outliving our warranties in the market. So what do batteries do? Well, let's have a look at the things that we can do if we have batteries on our solar system. One of the things we can do with batteries is we can shave off peak rates. So there are some ways that electricity companies will charge extra fees, and let's suppose that you're on a plan that includes peak use rates. So this is a peak demand. So if you're using greater than a certain number, and on the left side of your screen, you can see that I'm showing that there's maybe a peak higher rate charge if you go over about 60 kilowatts, right? So what batteries can do is allow us to produce some of that energy. We'll use some CTs to monitor how much power we're drawing from the grid and produce any excess that we need to stay out of this peak demand region by discharging the batteries and providing that power when that consumption starts to get near the peak rate. We can also avoid time of use rates. So here in California, I get charged much higher rates during the evening to pull my electricity from the grid. And what I do with my SimpliPhi system that's behind me is I charge up the batteries during the day when that solar is available. And even if solar is not available, I can charge from the grid. And then I can use that energy from the batteries during the evening time when electricity rates are really high and avoid all those expensive peak demand rates, which occur here between 5 p.m. and 9 p.m. You can also, if you have solar on your roof, like I do, you can charge your batteries up during the day and discharge them at night when you're really needing that power. So there are many ways to use storage. We're going to focus today on what happens inside the battery. So to start with, I'm going to talk about chemistry. So there are many different types of chemistry. The chemistry relates to the cathode material typically. And so I'm showing on the left side of the screen, there's LCO batteries, lithium cobalt oxide batteries. There's NMC batteries, which are probably the most popular battery other than LFP. Those NMC batteries are nickel, manganese, cobalt oxide batteries. These batteries are a little bit lighter. They're good for many purposes. They don't get quite as many cycles as you can out of LFP. And they're a little bit more prone to fire. So we've avoided them because we're a company that really focuses on safety, especially when you're going to have these batteries in your home, in your cabin, etc. LMO batteries are lithium manganese oxide batteries. LFP stands for lithium iron, lithium ferro phosphate. So ferro is the Latin word for iron. So lithium iron phosphate, that's the battery chemistry that we use. It is the best battery chemistry for home batteries. It's also the safest battery chemistry that's out there right now. NCA batteries are nickel, cobalt, aluminum oxide batteries. And the very last one that I've listed there, lithium titanate. We're not going to get too much into the chemistry, but that's actually a different anode. So the anode is the negative side of the battery, as I'm going to explain in a second. And these batteries allow for extremely fast charging and discharging, but they're also very expensive and not a good battery for home use. So we're using lithium iron phosphate battery chemistry, and we're using a form factor. So the other way that batteries can differ is what type of cell is used to make up the whole battery. So when I'm talking about an entire battery, it's often composed of many individual cells to get to higher voltages. And the form factor is the type of cell that's used in the construction of the battery. The cheapest cells that you can buy are pouch cells. These are quite common. I've got one right here in front of me. This cell came off of, this is just a dog collar. I just picked it up. It's got a little BMS on it. And I was going to show that, take a couple pictures of it. But that's a very common battery for a very low cost, not long life expected system. So you might get this inside a phone. You'll typically get this inside things that are only expected to last maybe 2, 3, 4 years. There are some slightly longer lasting cells, pouch cells that are being used for the construction of home batteries, but typically I wouldn't recommend them. They're prone to bubbling out. As you can see on the right side of the screen here, I'm showing this is an Apple battery that I pulled out of an iPhone that had burst when I went to check the phone and change the battery. I saw that the battery had bubbled out. And this is a common problem with pouch cells. They're laminated inside of aluminum foil, and the electrolyte can bubble and separate the layers.
Nathan.
So pouch cell, yeah, Daniel, go ahead.
So we had a question, sorry to interrupt you there on
No,
your
no
pouch
problem.
cells, but there's somebody's asking, in terms of residential storage batteries, which chemistry is least dependent upon non-USA materials? So which one can we source the best from here in the United States?
I think that's a great question. I don't know definitively the answer. I can tell you that lithium is fairly easy to mine. We can mine lithium here in the US, and I know we have lithium mines that are going in. They're also fairly safe mines because lithium is simply a salt, and so you can inject water down into the earth and pump that water out, evaporate it off, and mine lithium in that way. It's very similar to drying out seawater to get sea salt. For cobalt, cobalt is typically sourced in Africa, most often in the DRC, where mining practices are questionable. I've mentioned before in these webinars, I've spent 4 years of my life living in Ghana, which is where my wife is from. And mining there typically has many environmental impacts, some of which are just muddying and dirtying the rivers, which chokes out wildlife like fish that fishermen depend upon. So I would say that if you don't have cobalt in your batteries, that you're avoiding that cobalt typically sourced from Africa, but I'm not an expert on where this mining occurs. LFP batteries, iron obviously, and replacing cobalt and manganese is much easier to source. And the elements in lithium ferrophosphate batteries, the cathode, are found in our bodies, right? So the iron phosphate is very common. So I would say easily sourced anywhere in the world. Cobalt typically sourced in Africa. And I hope that answers the question, Daniel. So let's talk about the other kinds of cells. So we want to avoid pouch cells for installations that we're hoping to last for long times. And the other two options are prismatic cells, which have many good qualities. They typically come in very large sizes. These large sizes allow for lower costs compared to cylindrical cells, but they're almost always made out of plastic casing, and that plastic casing, especially with the geometries, ends up expanding and contracting more with time, with charge and discharge cycles. So when you charge and discharge a battery, it heats up, and that amount of heat causes thermal expansion. And if those batteries get too hot, that thermal expansion can cause separation of layers and other problems, breakdown of chemistry inside the batteries. And so prismatic cells don't last quite as long as cylindrical cells, but they tend to be a little bit cheaper. Kind of the premium battery cell that you can use is cylindrical cell. The cylindrical structure of a cell just offers the most amount of rigidity in terms of resisting expansion and contraction. Cylindrical cells offer, they're almost always hermetically sealed, which means they're completely sealed. There is a vent at the top in the event of high pressure that can open up and result in off-gassing. But otherwise, these batteries are completely sealed. And therefore, you get the longest life out of these batteries. They're better at getting rid of heat. Heat doesn't have as large a path to migrate. And so this is why we are using cylindrical cells. We're using the best chemistry. This is why we can offer the best warranty. So lithium ferrophosphate is what we use inside of our batteries. Inside the cell construction looks something like this. On the left side of your screen, you can see an aluminum foil roll separated from a copper foil roll by a porous separator layer called the solid electrolyte. It's just simply called a barrier, but then there's a solid electrolyte layer that on the first charge of the battery gets formed on that porous separator and helps prevent the flow of lithium between that copper anode layer and the aluminum cathode layer. On top of the aluminum is a coating of metal oxide. That metal oxide in our case is lithium ferrophosphate. And on top of the copper foil, we're using an anode. In our case, it's graphite. And that graphite, the movement of lithium between that metal oxide layer and the graphite layer is what allows power to flow from a battery. So what happens when we charge up a battery is that lithium prefers to be in the metal oxide layer. So we start off with a battery that has lithium in the metal oxide layer. And as we charge it up, we pump electrons off that metal oxide layer. That causes the lithium ions that are in the metal oxide to become free. The lithium can migrate through the porous separator layer, but the electrons cannot. And so the lithium ends up migrating over and meeting those electrons, which we pump from the cathode side over to the anode side through our charger. And so when the lithium meets those electrons inside the graphite, it intercalates, it works its way into the graphite lattice, and we end up with a charged battery of the lithium being over here in the graphite. If we remove the charger and put a load in the place of the charger, those electrons can flow back to the metal oxide layer, and the lithium can migrate through the separator layer to get back to the metal oxide. And that's how a battery cell works. It's not very complicated. If you can understand an internal combustion engine, you can easily understand the simple chemical processes that are happening here. And I like to present it even though it's not really part of the BMS. So what are we going to get into? Let's talk about some things that can go wrong with batteries. So lithium batteries, have gotten a bad rap. In the case of this Samsung Galaxy phone that was banned on flights almost 10 years ago now, maybe 7 or 8 years ago, the pouch cells that were in this phone could get overheated, which resulted in a fire. Now this is pouch cell, it's the worst kind of cell, but cylindrical cells can have fires too. And particularly in the event of something like a car crash, batteries can get damaged that can short circuit the inside of the battery. So if I imagine a puncture, which pushes the cathode and the anode together, rips the separator layer, maybe because of a big car accident, you can imagine batteries that are short circuited. There's energy inside those batteries if they're charged up, and you get that short circuit resulting in a rapid production of heat through the rapid discharge of the battery. That can result in individual cells that are damaged getting very hot. If they develop too much pressure, they can off gas, and that means to release the electrolyte. It's like an organic solvent that allows lithium to move. If that electrolyte releases, it can catch on fire. And if that cell gets hot enough, maybe you have the middle cell catch on fire, if it gets hot enough, it can heat up the cells around it. They can in turn off gas and heat up the cells around them. And that is known as thermal runaway. It's a chain reaction in which one cell heats the next cell, which off gases, which catches fire, which heats the next cell. The good thing to know is that with LFP batteries, and in particular our batteries, right, our batteries have essentially no risk of unmitigated thermal runaway. If we get an individual cell to off gas, and this is shown in our UL tests, that our batteries self-extinguish. Let me show you something else. Here are two pouch cells. These are comparing NMC chemistry, which there is a place for NMC chemistry. If you're building something that needs to be lightweight like a drone, you're going to need to use a lighter chemistry. But note that there's a much greater fire hazard for NMC chemistry. So what I'm showing you here is Will Prowse from Do It Yourself Solar. He punctured two different cells, one an NMC cell and another an LFP cell. When he punctured the NMC cell, within seconds, it starts off-gassing due to the short circuit. So he actually drilled a hole in it, right? And then it bursts into flames within about 15 seconds. I'm showing you the screenshot here from his video, but I'll have that link here and you can go and watch that video yourself. In comparison, he took a pouch cell with LFP chemistry, drilled holes in it. He had to drill almost 10 holes before the thing even started to off-gas. Finally, it did off-gas, but as you can see, if you watch the video, this is basically all you get, a little bit of smoke. It's a much longer, slower release of energy from an LFP off-gassing event. So there's safety factors that you should be taking into consideration when you're installing batteries in homes. And because of these safety factors, I really believe, not just saying this because I'm working for Briggs Stratton, but I really believe you should only be using LFP at this point. In the future, maybe we'll have solid state batteries and we'll have other options, but right now, the only chemistry I would put in my home is LFP. So there are a couple things to talk about with temperature. During thermal runaway, electrolyte can vaporize, and this only happens when it gets so hot that the liquid electrolyte can turn into a gas. And if this gas is contained within a cell, that cell can rupture a vent and cause that gas to escape, and that gas can burn. That gas is toxic, and it's more toxic depending on which type of chemistry you have. But the point to note is that for LFP cells, they can reach much higher temperatures without thermal runaway beginning. So about 30 degrees Celsius hotter, 200 degrees Celsius versus 170. LFP also has a much lower maximum temperature when off-gassing happens during a thermal runaway. So if you force it to go into thermal runaway, you're looking at a maximum output temperature about 400 Celsius. And with NMC, that maximum temperature is considerably higher. So one more reason, to avoid that cobalt-based battery cell for home installations. How do we get to higher voltages? How do we get to 48 volts? Well, an LFP battery cells have nominal voltages. That means a named voltage. The voltage varies slightly during the charging cycle. But that nominal voltage is about 3.2 volts. That means the voltage of the battery cell when it's 50% charged. How do we get to 48 volts? Well, the way we would get to 48 volts is we take 16 of these LFP cells, put them together in series, right, inside a battery. So the typical battery that's being built, I'm showing you one of the larger batteries here. This is an AmpliPHI battery. It's got stacks that are packs of cells which are arranged in 16S configuration to produce 48 volts. Well, if you have that many cells in series, you're going to have to pay attention to the weakest link in the chain. You need to make sure that all the cells maintained a balanced charge and that those cells are monitored during a charging and discharging event. And so what does that? Inside the battery, in addition to all these cells, all lithium batteries have a battery management system. And inside this battery at the very top is a very sophisticated and high-end BMS unit that we use to allow for communication, balancing of charge, and temperature monitoring, many other things. So we're going to get into that. That's the point of today's talk. We also incorporate in every one of our batteries a breaker so that you can switch it off, isolate different batteries when you're doing setup. Makes it easy to turn the battery off when you're connecting cabling, etc. Daniel, how are we doing with questions?
There was a couple came in, a couple around surge protectors on systems, and we put in the chat. Midnight Solar makes some great whole home surge protectors.
Thank you, Daniel.
No other questions.
Thank you. So let's jump into what the battery management system does. Okay. So first, I want to address one thing that the battery management system cannot do. The battery management system is not a valve that can regulate current flow. If you have a device, a charging device that's trying to charge the battery within the rated specifications of the breaker on the battery, and for AmpliPHI batteries, that's 100 amps. For SimpliPhi batteries, it's 100 amps. And for our Phi batteries, it's 80 amps. If you're within that range, the battery cannot regulate how fast current is flowing in, right? What it can do is protect itself by opening up a contactor, and I'll talk about that. But you need to make sure you're using appropriate charging equipment. A lot of people think that the BMS is responsible for controlling the current into the battery. No, that's your charging equipment. That's your charge controller. That's either built into your hybrid inverter, or it's an external piece of equipment that's maybe hooked directly to your solar, etc. So the BMS does not do that. But what it does is it pays attention to a deep cycle lithium battery, makes sure that the cells are balanced, makes sure that the temperature of those cells is within specifications, etc. So a BMS manages and protects the battery from functioning outside of its safe operating parameters. It can monitor various environmental and system-based conditions such as voltage, cell temperature, amperage, state of balance, state of charge, etc. It can provide programmable communications capabilities as well. So a BMS can offer the ability to change settings, to talk to external equipment, and it can also control thermal management systems in some cases. The main purpose of the BMS is to protect that battery, to keep it running in its designed operating parameters, right? So that we can access the full capacity and the full longevity of the life of that battery. Lead acid batteries are very simple batteries. Lead acid batteries typically do not have a battery management system. They do have an electrolyte, and that electrolyte is sulfuric acid. And that's with lead acid batteries was typically very, very problematic, right? The water would evaporate, resulting in a much more concentrated acid, and you would have to water these batteries. The nice thing about lithium batteries is they're not, they don't need servicing, right? They don't need monitoring of electrolyte. Pretty much once you install this battery, get it programmed properly, it will be easy to use, but easy to be used and maintenance free, but it does have a built-in BMS. So lead acid batteries did not have BMS systems built in. Lithium batteries do. All lithium batteries do, even the cheap ones, right? So the battery management system has to ensure that the capacity is available for each cycle, and making sure that we don't have weak cells or weak parallel stacks, preventing the full amount of life. It's going to protect that battery from abuse, and it can help prevent thermal runaway. So battery management systems come in a variety of forms. Analog BMS systems basically do not have user interfaces. Their values are programmed during manufacturing. It's basically designed to operate and set to operate under a set of circumstances that are controlled during the manufacturing process. And they don't have as many integrated components, such as programmable chips, etc. They're based on electrical signals. Their performance is based on electrical signals, and not communication signals. Typically rely on values of the components to take or not take actions, and they often do not transmit. They don't transmit data to other systems of equipment that might be in a energy storage system. Digital BMS systems, which are found on higher end batteries, offer a lot of different features. Some include temperature monitoring. I'm showing, this is not one of our BMS units. This is one I had bought from Overkill Solar on a battery build that I had done. And I'm going to point out a few things about it, but it's programmable. They offer balancing of the cells. They often offer software capabilities so that you can monitor, etc. They take digital inputs and convert that into electrical signals to take action. They may or may not transmit data. The one I'm showing here does. This is a Bluetooth antenna that's here, and Bluetooth dongle to allow Bluetooth communication directly from your phone to this particular BMS. Our BMS is even more sophisticated and much higher end than this one, but I'm showing this one as a simple example of something that you can buy. Batteries with digital BMS may also have some analog BMS as a fail-safe as well, such that in the event that some of the communications equipment or settings get out of range, that they can still operate on a basic mode. What do we offer in terms of batteries at SimpliPhi? We have both low and high voltage options, right? Our Briggs Stratton batteries start out at 12 volts. We have small batteries at 12 volts. We have larger 5 batteries at 24 volts, and there are still many legacy pieces of equipment that are using 24 volts. Typically, mobile applications use 12 or 24 volts still, and so we do make some batteries in the 24 volt range. The most common and really the industry standard for home battery backup is 48 volts, and we have a variety of options in 48 volts that we'll get into. I'm showing the AmpliPHI battery here. It has closed loop communications as well as device port to communicate to different devices through CAN bus. And we have many options there for our 48 volt that we'll talk about. On the high voltage side as well, we have batteries that go up to 1200 volts. You may not know this, but we have a whole high voltage range of batteries at Briggs Stratton Energy Solutions, and we're going to have upcoming options for the 30 and 60K systems from Solarc. So those are under development. If you have interest in very large battery systems, talk to us about our high voltage and large projects division. We have containerized solutions, etc. In the high voltage stacks, each battery has some communication through the cell interface, and the cell interfaces connect with a stack controller, which maintains balancing and other communicating needs for the whole stack of batteries. Our batteries come in, Daniel, what's the size? Is it 4.3 kilowatt hours per battery?
Yep.
For our high voltage?
Yeah, 4.3 kilowatt hours, either 24 or 48 volts. We did have a question, and I'm not sure exactly the context here, but David's asking, what is considered to be a weak cell?
I think you're asking about a weak cell. So with a lithium battery, first, a couple of things. When you manufacture a lithium cell, there are slight variations in surface area. There are slight variations in the amount of lithium that's in there. And so low quality cells maybe from the cheapest of our competitors, can vary by 5 to 10%, right? And if you think of a battery, like a 48 volt battery, as a chain of 16 cells. Now, really, the battery that you see on your screen on the left side there has closer to 300 cells in it. But if you think of it as a chain of 16, if you have a cell which has slightly lower capacity than all the other cells, because all these cells are in series, the cell with the smallest amount of capacity is going to limit the amount of current that's able to flow through it, right? And so a weak cell would be a cell that has a little bit lower capacity than the rest of the cells. At SimpliPhi, we use premium cells, and we often have less than 2% variation in capacity. And then we sort those cells so that our cells have matched capacity on each stack. So we very rarely have big variations, but cheaper batteries, you often will have slightly lower capacity cells, and those can affect the total output of the battery, especially if they're not topped off and each cell doesn't get balanced. I hope that answered the question in terms of lithium batteries. Lead acid batteries, weak cells are similar, right? You can have variations on the lead plates, which result in individual cells not producing as much as others. And so typically the same thing with a 12 volt lead acid battery, you've got one cell that might have diminished capacity, and that affects the output of the entire 12 volt battery, which has 6 of those cells. If I didn't answer, please ask further.
David says, excellent answer, thanks. We have another question. It's asking about how we balance the cells using resistors. So I think we're coming up onto that slide here just in a second, so we'll give you a chance to answer that.
Yeah, I'm going to come up on how we balance the cells here. And Daniel, so just for a little bit of a preview, balancing of cells typically happens in the last part of the charging cycle. So when the cells are at 90% or above state of charge is when balancing happens. And it's at that point where we're trying to make sure that each of the cells reaches that same voltage. And I'm going to talk about how that happens. So Daniel's right, it's better we hold for just a minute and I'll talk about that. So let's talk about different ways to balance cells. So you can imagine what I'm showing you here is just 4 battery cells on the left side of your screen, negative to positive going from bottom to top, 4 cells arranged. If these were typical alkaline cells, maybe 1.5 volts each, this would produce, well, 4 times 1.5, so 6 volt battery, right? With LFP cells, 3 times 3.2 or 4 times 3.2 volts, so you'd be at a nominal 12 volt battery. But the way this works is we want to charge all these cells, and to charge all these cells, we would run a current vertically down from the positive plates through the negative plates in series. But what would happen if maybe cell number 2, which I'm highlighting here, had a diminished capacity, so that maybe the other cells could take 5 amp hours worth of current, but cell number 2 started off at maybe a different percent state of charge, or maybe just didn't have that full capacity. And what would happen is this cell would fill up before the others. And so as soon as this cell would get at 100% state of charge, it would not allow any more current to flow through it. And so you can imagine that one way we could get the other cells fully topped off once this one is already full is to bypass that cell. And so the current could come down through the first cell, pass out through a resistor, out through a diode and back through around cell number 2, right? By going around cell number 2, I can get to cell number 3. And so I could follow this pathway where I go out through a resistor, in through this diode, through another resistor, around cell number 2, and then the current can flow through cells 3 and 4. This is called passive cell balancing. It maintains a capacitor there to prevent small oscillations. It's not a good way to do it. Why is it not a good way to do it? Well, this is the cheap way to do it, right? It's not a good way to do it because if you're passing current through a resistor, what does that produce? Heat, right? That's what resistors do. You know, they limit charge flow by the production of heat in the buildup of a voltage across the resistor. And so if we do it this way with passive cell balancing, we end up producing more heat. We do not use this type of cell balancing, but other companies and lower cost solutions can. What's a better way to do it? We could do active cell balancing. So let's suppose we just had 2 cells in series here, maybe a little bit easier to visualize. If I'm passing a current down through cell number 1 and to cell number 2, and cell number 2 maybe happens to have a lower voltage than cell number 1, what I could do is use these charge shuttles by flipping these active switches back and forth. When that switch is in the top position, it can charge this capacitor. And so if the 2 switches, switch 1 and 2, are both in the top position, the voltage of the capacitor would match the voltage of cell number 1. If these switches flip into the downward position, that same capacitor, which had charged up off cell number 1, would now be in parallel with cell number 2. And so with the switches in the downward position, the capacitor would discharge, if cell number 1 was at a higher voltage, into cell number 2. This is the more sophisticated and much better, much more efficient way to charge battery cells up. And this is the type of cell balancing that we use through our BMSs. It's much more sophisticated than this, and it's digitally controlled. But this is essentially how higher end BMS units can charge up the individual cells once they're in that balancing state, and do it efficiently. Notice we're not using any resistors here to slow the current down. There is, of course, a little bit of resistance, but it's not the same. We're not using that same way of just bypassing each cell with resistors, which results in a lot of heat. So internal analog BMS do not have the big difference is that they don't have communications. They're not easily controlled, and so there are still very advanced BMS units that go into our PHI batteries. But these units don't offer closed loop communications and don't offer individual information about different batteries. There's still a good place for these. A lot of people love the PHI batteries because you can use external equipment to provide many of these sources, these abilities with batteries. So with an analog BMS, with our PHI batteries, you can use external equipment. Like this is a temperature monitor here. We often recommend the BMV 712 from Victron. It is when they're labeled BMV 712, the smart here just means Bluetooth. So with this piece of equipment, you can communicate with it through your phone. This can monitor batteries. It doesn't do quite as good a job as our communicating BMS units do. But you can program it to fairly well compensate for temperature. You can program their smart charge controllers as well. What we're showing in the bottom left is the Schneider SCP, which allows similar functions. And some of the most important things to include when you're programming your charge controllers to work with PHI batteries, non-communicating batteries, are to properly put in the LBCO. The very lowest we recommend that you set your LBCO would be 48 volts, and that's for 100% depth of discharge. So LBCO is low battery cutout. You don't want to discharge your battery beyond that. In fact, once you get down to 48 volts, there's almost zero energy left in the batteries, right? So we often recommend, Daniel, 50.1 volts is our 80% depth of discharge. We often recommend that you use 80% as your depth of discharge at 50.1 volts for LBCO. And the reason for that is you get a lot more cycles when you don't cycle your battery all the way down to 0%. Cycle it down to 50.1, you'll get 80% of the use out of your battery, the available energy out of your battery, but you're going to get 10,000 cycles out of that battery. If you're cycling once every day, that'd be 27 years. It's a very, very long time. Just to point out the big difference, if you cycle it down 90%, which is 49.6, I believe, if you cycle it down to LBSCO of 90%, you get about 5,000 cycles. That's more like 15 years. And if you cycle it every time down to 0%, we're expecting closer to 3,000 cycles. Now, we know that there's going to be a large variation of those cycle depths, but and you won't always cycle it down to 0, but if you did, those are the number of cycles we would expect. So we do recommend that you use a 50.1 LBCO, but you can go all the way down to 48, and the warranty for 15 years is there no matter what. The voltages, we recommend looking up the appropriate bulk, absorb, and float voltages. Those are the voltages used during the charging cycles. The bulk part of the charge cycle is that constant current part. The absorb portion of the cycle is just 6 minutes where you're topping off at 56 volts. That's where you go from 90%, 95% state of charge to 100. It's also where most of the balancing is occurring. And then the float is just a very slow charge where sometimes it's in a charge cycle. And if you have a renewable energy source like solar, you could float at 54 volts.
Nathan.
Yes.
We do have a couple good questions. Wallace is asking, what is the preference between every charge cycle going to 100% versus daily 90% charge with occasional 100% cycle? If occasional, how often to push 100% as in the absorbed volts for the 0.1 hour?
That's a great question. And so for LFP, as long as you use our 56 volt recommended absorb, there's essentially no difference. The number of cycle lives doesn't get influenced by that 56 volts very much like it does with NMC batteries. So Tesla, for instance, has 2 types of battery cells. They offer NMC cells, especially on their longer range vehicles, because they're a little bit lighter. And they also offer LFP batteries. And one way to know what kind of Tesla you have is if it tells you not to charge your car above 90%, unless you're going on a long trip, then you have an NMC battery pack in your Tesla. NMC is much more influenced by that high voltage side of the charge cycle than LFP is. And for our LFP battery chemistries, we don't have specific numbers from our engineering team on cycles depending on the top of the charge cycle. It has a much greater impact on the bottom side of the charge cycle. So for LFP batteries, we have to worry more about what we're discharging to. That being said, no batteries like being charged above the voltage that they should be set at. We should not have any voltages above 56 volts for our 48 volt battery nominals, and you should not have anything above 28 volts for our 24 volt batteries. So hopefully I answered that question. I don't think that we don't have a preference for only charging up to 90% state of charge for our batteries because they're LFP, not NMC. But on the discharge side, it does make a difference, the depth of discharge. Okay, so let's move. The maximum charge and discharge current is dependent on the battery. I'm gonna show you those in a second. I also want to show you closed loop communications. So there are a couple of things I want to point out with closed loop communications and common mistakes when installing these batteries with the communications equipment. So first off, there is a cable that is used to allow individual BMS units from individual battery modules to communicate with the other batteries in the system, the other battery modules. They're strung daisy chained together essentially with Cat5 cables. So you're essentially just going to run a communication cable from the battery port on one battery module to the next battery port on the next battery module. Same thing for that second battery to the third and the third to the fourth. No battery modules should have an empty plug. If there is an empty port because there's no battery to the left of battery number 1, you should put a terminating resistor here. And that terminating resistor allows the batteries to know that is the end of the CAN bus chain, right? There's nothing to be communicating there. And I think it's just a 100 ohm resistor. Daniel, do you know for sure, is that just a 100 ohm resistor inside that network terminator?
Yeah, I'm not sure the value, but it's a resistor.
Is a terminating resistor. So just note that if you're installing, a lot of times we'll get installers that are doing their first communicating batteries, and they've accidentally thrown out this little terminating resistor. It comes with all of the batteries, so just make sure that you don't throw that out. It comes in a bag with the Cat5 cable. These are included with our batteries. So when you unbox them, you'll see that in a bag, and just make sure that you know what to do with it. Looks like a little thumb drive. So the other thing to note is that only one of the batteries of the chain needs to be connected with communicating equipment. So for instance, if you were installing one of our ESS systems with our communicating batteries, you would install one cable coming out of one battery and go to our gateway. If you have a communicating inverter like a solar arc, you only need to connect one of the device ports of the battery to the inverter. So there are battery ports on each battery, these two, and then there's a different port that's labeled device on each of the batteries. And that device port goes to the communicating equipment like a charge controller or an inverter. So want to point out a couple of things about the install here. Here we're showing the use of bus bars. And so bus bars are a great way to connect batteries up. I had somebody call in yesterday and was asking about connecting, why we don't recommend connecting with cables. The reason is that the bus bars that we offer have a lot larger cross-sectional area for current to flow through, and that minimizes any difference in voltage that the individual batteries see. When batteries are run in parallel like this, the ones closest to the connectors see a slightly higher demand for power out of them compared to the ones in the middle. Notice also that what are we doing with the bus bars here, Daniel? We're coming off of, what are we doing with the bus bars?
Yeah, we're coming off opposite ends, so we're not making one of those batteries work harder than the other.
Great. So notice that we've come off opposite corners for the bus bars. We're taking the positive off the top corner here and the negative off the bottom corner. And what that does is it makes it completely symmetric for the front two batteries here closest to the connectors. Now, in truth, the middle battery here is going to have it the easiest. It's going to see this, it's going to discharge a little bit slower than the batteries on the ends. But because we're using bus bars, that difference is minimized. And the reason we don't encourage the use of cables to connect the batteries is because you can see significant differences. There's a little bit more, everybody uses stranded cables, but stranded cables have a little bit more resistance to them. They are flexible. That's why we use stranded cables like welding wire or just heavily stranded cable for batteries, 2-aught, 4-aught. But we don't recommend using those. If you're going to put batteries in parallel, we recommend the bus bars or cabling of equal length to a combiner. Here's what it looks like for one of the high voltage stacks. So again, these stacks can go all the way up to 1200 volts nominal DC. The 48 volt stack is what I'm showing here. You can tell because it has a stack controller on both of the stacks. A 24 volt modules you only need a single controller for 2 stacks. But these can go all the way up to 1180. Almost everything that is requiring 3-phase 480 service is a good fit for these high voltage stacks. And again, they can come in very large systems where it comes in 24-foot shipping container or even a 48-foot shipping container. And we have solutions if you have very big projects like that. The cell interfaces allow communication between the individual modules. You can see those communicating cables running up here. And then the stack controller is controlling the overall charging of this system and monitoring. So let's understand the basics about battery systems. So one of the things that often people, especially homeowners that are getting into batteries for the first time, don't realize is that in addition to amount of energy that batteries can hold, there's also an amount of power that they can output. And I like to use this example. I'm showing a water tower that I built with some students years ago on a project in Ghana. And I'm showing the water tower for a good reason here. So what's here is solar energy that's running a sun pumped water pump, and that's run through essentially an MPPT that maximizes the solar energy going to the pump. The pump pumps water into the tank, and then that water tank is there for storage. Well, I want you to think of the energy inside a battery similar to the water inside a water tank, right? There's a certain amount that's held. There's a certain amount of energy in a battery. There's a certain amount of water that a water tank can hold. That's the capacity of the battery. We typically refer to the capacity in kilowatt hours, or for very small batteries, watt hours. And we might use gallons or liters for tanks. But there's also the thing that's often forgotten is how quickly you can get the energy out of a battery. There's a power rating on batteries. Our batteries have a fairly fast power rating, fairly high power rating. It's C/2 discharge cycle, which means you can take all the energy out of the battery in 2 hours. The same with charging it, you can charge it in 2 hours. So there's a power limitation on batteries because all of our batteries are rated at C/2. If you know that you have a 5 kilowatt hour battery with us, the output power of that battery is over 2 hours. So 5 kilowatt hours divided by 2 hours is 2.5 kilowatts. So half of the battery's energy capacity would be its power output. Homeowners often don't realize you can't take all the energy out of battery very, very quickly, right? There's a power rating. Well, you could say the same is true for a water tank, right? You can't fill that water tank in 10 seconds. You would burst all your pipes. You would have to have such a high pressure to put that water in there. The same with batteries. You can't charge that battery in 10 minutes instantaneously, right? Because you would rupture you would ruin all the chemicals inside the battery. You would melt your wires, etc. So we have to pay attention to that rate. So let's talk a little bit about the specifications of batteries. There's the energy capacity of batteries. It's the amount of energy that a battery can hold, typically measured in kilowatt hours, and it's often specified at a certain rate. So you get the most energy out of a battery if you discharge very slowly. The faster you discharge, the more amount of heat that you produce. This is known as the Poincare effect. But basically, it's simply understood in terms of Ohm's laws, right? Ohm's law says that the amount of heat generated is I squared R, right? The square of the current. And so the slower you do it, the lower the current, and less heat you generate. So the energy capacity of our batteries are specified at a C/5 rate. That means if you discharge the battery over 5 hours, you'll get that the energy rating of your battery in terms of energy output. So if you have a 3.8 kilowatt hour battery, you discharge it at 1.9 kilowatts. That would be a C/2 rating, right? You get a little less energy out of it if you discharge at that rate. Current capacity, that's the amount of charge a battery can deliver. It's the amount of current a battery can deliver in terms of current times time gives you charge, which is in amp hours. So often our batteries have an amp hour rating to them. So our 48 volt Phi and AmpliPHI batteries have a 75 amp hour rating to them. And what that means is they can deliver 37.5 amps for 2 hours, or 75 amp hours total. That doesn't vary. That isn't specified. That's a certain amount of charge. Nominal voltage is the voltage of the battery. People use this word differently. Nominal voltage for us means the voltage of the battery at a 50% state of charge. For us, that's 51.2 for our 48 volt batteries, and half of that for the 24 volt batteries. C rate. C rate for batteries is how quickly you can charge or discharge them continuously. So the C rate on our batteries is C/2, and that's true for all of our batteries. So there's an example on the screen there.
Nathan.
Yes.
So it's 120 ohms.
Thank you.
And this might
That's the terminating, Danielle's referring to the terminating resistor values, 120 ohms. Thank you.
Yes, yeah, exactly. And this may be a good time to address this question. Fred's asking, what is involved in converting an existing system from lead acid batteries to LFP? And I thought this might be a good screen because we're going to talk about C rate and how they're not the same.
Yes. I'm smiling because we're going to do an upcoming training on lead acid conversion. And so there are a couple of things. So first, you have to make sure your charging equipment is capable of charging and discharging lithium batteries. You want to make sure that you can appropriately put in those voltages and set points for lithium in terms of what that charge cycle looks like. So we'll have an upcoming training on that. But that's one thing. The other thing to keep in mind is lead acid batteries were often specified in terms of their capacity in a current capacity, right? So you'd say, oh, I bought a 200 amp hour lead acid battery that's 12 volts. Well, 200 amp hours, sure, that's the total capacity of the battery, but for lead acid, you would only discharge those batteries typically down to about 60%, maybe 50% state of charge if you're working them hard. So unlike lithium batteries where you can charge them all the way down to 0% state of charge without really doing much damage, with lead acid battery, you could never do that. So one would be understanding how much capacity you actually need, right? Typically, you're going to get much more usable capacity out of a lithium battery. Two, make sure your charging equipment will match. Three, make sure that you're going to appropriately connect the lithium batteries to the charging equipment to avoid imbalance if you've got more than one battery. Daniel, would you add anything to that?
No, that's a great point. Thank you, Nathan.
Let's look at the example at the bottom when we're talking about C rate. I want to make sure everybody understands C rate because a lot of batteries, our competitors' batteries are typically rated at C/3, which means they could charge or discharge in 3 hours. Ours can do it a little bit faster in 2 hours, but it's important to make sure that you don't exceed this rate, especially continuously, right? Now, our batteries are capable of surging, but they can't surge continuously for a full discharge cycle. So let's look at the example, a 20 amp hour battery that can safely deliver 10 amps, right? So if it's a 20 amp hour battery, if it's delivering 10 amps for an hour, right, then it would take 2 hours to discharge, hence C/2 rating for that. Voltage is approximate, right? So it's approximately constant, right? So a C rate is really pretty close to the power output of a battery. If we have a 48 volt battery, it's going to stay, pretty close to that 48 volts during a discharge cycle. Typically, you're going to be closer to maybe 52 volts when you're discharging. And so if you're 10 amps at 52 volts, right, then you would be getting 500 watts out of that battery, or 520 watts. Any questions about these definitions?
No, we do have a couple of great questions. I'm going to save them till we get to a little bit end, and let's keep going. Thank you, Nathan.
Okay, so let's talk just a little bit. So I have talked about these high voltage battery stacks. I talked about our containerized solutions through Briggs and Stratton. We also have some mobile options in terms of, this is basically a battery version of a generator. It's got a charge magnesign controller built into it. It's got a couple of our PHI batteries and an inverter built in. And so you could use this on something like a construction site. Maybe you can't run a generator because you're in an HOA where generators aren't allowed, and you want access to power. This comes on wheels, etc. We also have these access cabinets. We're essentially plug and play cabinets. We're showing this here with a solar, because it's a really common product for us. A lot of people desire these kind of all-in-one packages, all the wiring's built in there for you. It's kind of plug and play. We also have a number of our different batteries from Briggs and Stratton here. I'm showing you the PHI battery, AmpliPHI battery, even one of our 12 volt options there. And this is our bigger 4.9 wall mounted outdoor rated battery. So if you're interested in an outdoor rated battery, you've got it. Our smaller batteries come down in as small as 1.4 kilowatt hours. And these are great for mobile applications. And then typically these are 33 pounds or 17 pounds for the even smaller one, down to 0.73 kilowatt hours there. And so those come in different voltages, 12 and 24 volt. The PHI battery specifications, the PHI batteries will come in a 24 volt version with 151 amp hours, or a 75 amp hour 48 volt version. And so both of these are very common, especially for lead acid replacement. They also do come with wall brackets if you're interested in wall mounting these. We have battery boxes that house these, that have temperature controlled fans in them. We have heating options for these batteries. If you're going to install in a cold environment, we have temperature solutions for those, and we have an upcoming training on that as well. Our communicating batteries come in two flavors. Our AmpliPHI battery only comes in a 48 volt version. We have no 24 volt version for this. got UL certification on this. I've gone through integration with Solar here. It integrates well. The system behind me is running off of 3 of these AmpliPHI batteries with the SimpliPhi inverter as well. The wall mount SimpliPhi 4.98 kilowatt hour battery. This is essentially 5 kilowatt hours, hangs on a wall, very easy to install, larger format for bigger installs. And this is a slightly heavier battery. We're looking at an increased size. And then there's this, this is an outdoor solution as well. So if you want to mount this on an exterior wall, if you're not in a very cold climate, this is a good option for you. Because it's got waterproof communications ports, waterproof lugs for the batteries, and there's a conduit box that can come with this as well. It's got the integrated breaker, and though this is heavy, it's fairly easy to install. It's got these built-in handles on it to make it easy to install. All of our larger batteries have those.
And Nathan, we did have a question about, are there any ambient temperature restrictions on our batteries? So yes, we do. On our the standard Phi battery, the AmpliPHI and the SimpliPhi, we can discharge down to -20 centigrade up to 60 degrees centigrade. Now on the charging side, we're more limited on the Phi battery. We can go down to 0 degrees centigrade up to 50 degrees centigrade for charging the Phi. But with the AmpliPHI and the SimpliPhi batteries, the one that have the closed loop communications, we're letting you get charge those at a much colder temperature, down to -20 degrees centigrade, up to 70 degrees centigrade. Why is that? Why is it that the communicating batteries can be charged at a colder temperature?
Well, that's a great question, Daniel. And actually, in the last 20 minutes here, I am going to get into that. But I'll essentially spill the beans here. It's because the communicating battery can tell the charging equipment what rate it should be charged at based on the temperature inside the batteries. And so I'll get into that here in just a couple of slides. I'm just going to point out these battery cabinets for people. So if you're looking for kind of a complete solution that's outdoor NEMA 3R rated, you might consider one of these battery cabinets. The battery cabinet on the left is a 6 battery cabinet. That's a Boss 6. You can get 23 kilowatt hours essentially there. 46 kilowatt hours in the 12 battery version. That's a Boss 12 here in the center of the screen. And then, as I said, these access cabinets can come with 11.4 kilowatt hours up to 23.6 kilowatt hours in a complete plug and play type of solution. A very common request is to get a 12K Solar in one of these cabinets. And like I said, it's a very easy install to do. So let's talk, before I get into those, the temperatures for the charging, Daniel, let's talk briefly about what a typical charge cycle looks like. And this is true for about every battery, every lithium battery that's out there. So there are 3 parts to a charge cycle. There's the bulk portion of the charge cycle, which is done at a constant current. So I'm highlighting the bulk portion right here for our AmpliPHI battery or our Phi battery, which is shown here in the left. That's 37.5 amps per battery for those batteries. Those are more common batteries. So the bulk portion occurs. Notice that the current is just flatlined at a constant value here. That's the bulk cycle. Now, if you had 2 batteries, you would double that 37.5 for 75. If you have 10 batteries in parallel, it would be times 10. So you could charge 10 of these batteries at 375 amps. But that's done in a constant current. Now, as long as your charging equipment can maintain that current, so if you're running off of solar and it's not able to produce that full current, it will charge as fast as it can up to that limit at a constant current. But notice, as we start to charge a battery up, what happens is the voltage that we have to apply to charge that battery starts to rise, right? So if I'm putting 37.5 amps in a fully discharged battery, I don't have to apply a very high voltage to get that. I might be able to do that at 52 volts. Right? But to apply that same current when that battery gets more and more charged, I have to apply greater and greater voltage on the charging equipment. And you'll see that voltage start to rise as those batteries are charging up. We set the end of the charge cycle at what's known as the bulk voltage, and that's 56 volts max. So once the charging equipment hits 56 volts, we are done with the constant current bulk portion of the charge cycle. At that point, the battery will probably be close to a 90 to 95% state of charge. The next portion of the cycle, we're just going to hold at a constant voltage, and that current will continue, but it will drop off and get lower and lower and lower as that battery nears 100% state of charge. So at the end of the absorb cycle, you're pretty close to 99 to 100% state of charge. If you have a renewable energy source, you could float that battery to just keep it topped off. Maybe you've got excess solar and you're just going to float that battery at 54 volts. So you're going to use a constant voltage to float. Daniel, there was another portion of a charge cycle for lead acid batteries. Do you remember what that was called?
The fourth cycle?
Yep, the fourth portion of the cycle. I'm blanking on the name right now.
We called it equalize.
Equalized, right. And the equalized you do not want to use for batteries. The equalized portion of a charge controller cycle was to apply a very high voltage for a short amount of time. Typically it's done once a month. And the deal with that high voltage was to burn off that sulfur that could build up on the lead plates. Do not use equalize on a lithium battery if you're using older legacy equipment. So just keep that in mind. So thank you, Daniel. So here are the three different types of batteries. I'm listing the charging characteristics of each. On the left, we've got a 48 volt phi battery, or sorry, 24 volt phi battery. The amp hours are higher because the voltage is halved. So more current through these batteries, you get more battery cells in parallel instead of series, right? And then the stacks are arranged a little bit differently inside the 48 volt phi batteries. So you got 75 amp hours here. These batteries will charge at a maximum rate of 37.5 amps. So if you have a 150 amp hour battery, C/2 would be half that, or 75 amps per battery. So if you're running 24 volt, you can use higher amperages for charging the batteries. The communicating batteries, the AmpliPHI and the SimpliPhi batteries, are only coming in 48 volt varieties, and a C/2 rating for them would be 37.5 for the 3.8 kilowatt hour AmpliPHI battery, and 48.5 for the 4.98 kilowatt hour SimpliPhi wall mount battery. On the discharge side of things, these batteries can actually surge, so you can get 80 amps out of the Phi battery, both varieties here, the 48 and the 24 volt, and that amperage is really limited on the 24 volt to that fuse and the BMS there. So again, 80 amps surge out of the Phi battery. You can get 100 amps out of the AmpliPHI battery. You can do that for up to 10 minutes. That's the maximum this battery will output, but typically this battery will be sitting at 53 volts fully charged. So you can get over 100 amps at 53 volts, would be over 5 kilowatts of power out of a single battery. You can do that for up to 10 minutes for a real surge there if you need a lot of power for a short amount of time. The SimpliPhi battery can also surge up to 100 amps for 10 minutes. Again, limitations based on the breaker and the BMS there, but that's a huge amount of power out of these batteries for a limited amount of time. Let's talk briefly about state of charge and voltage. Just keep in mind when you're in a charging cycle, that the voltage will actually not be the battery's voltage, right? It will be the charging equipment's voltage. And when you're in a discharge cycle, the voltage will be below the battery's rest voltage, and that's due to current flow. So on the right side of the screen, I've kind of showed you a very simplified wiring diagram, I guess, in which you're looking at a schematic here. And if you look at a battery, the battery cell itself has a certain voltage across it. But when a battery is in either a charge or a discharge cycle is shown here in green, discharge cycle in blue, the battery's voltage will be different from the resting voltage. It will be different from that voltage of the individual cell. That's because there is some resistance inside the individual cells. And so if you're discharging across a cell, you'll lose some voltage due to the internal resistance. When you're charging across a cell, you will gain some voltage across the internal resistance. This is a point I'm trying to make here. So first off, if we look at what the state of charge curve looks like for a battery, for a resting battery, which you have zero current coming in or going out. So you discharge it, you disconnect it, look at its voltage. You discharge it a little more, disconnect it, look at its voltage. And you'll see this voltage start off around 53.2, 53.4 for a fully charged resting battery. Don't be confused. We charge up to 56 volts. That's the charging equipment's voltage, right? As soon as that charging equipment stops the charge cycle, will come down to the voltage of the battery. And it takes a few minutes maybe to come down. So you're going to charge up to 56 volts, but once we disconnect the charging equipment, you'll start off here around 53 to 54 volts fully charged. And then as we discharge the battery and let it rest, you'll see that voltage drop off. So you can see at a 50% state of charge, a resting battery would have a voltage of about 52.4, 52.5 volts. Okay. Once we get down to a 10% state of charge, we're around 51 volts for a resting battery. It will be a lower voltage for a discharging battery. So I'm going to show you that in a second. So notice that these are the characteristics for a discharge voltages. So if I'm looking at 52.4 volts for a resting voltage, that's a 50% state of charge. When I'm discharging, I'm losing some voltage across the internal resistor, so there'll be a drop. Typically, this drop is about a couple of volts during a very fast discharge, like a C/2 discharge cycle. So keep that in mind. So I'm going to show you, this is what a curve looks like for different discharge rates. When I'm discharging fairly slowly at a 5-hour discharge rate, C/5, right, I can see the voltage is not that different from a resting charge cycle, but I'll be below 53 volts even when I'm close to 100% state of charge. Right, so it's typically about a volt below on a C/5 discharge curve. And so notice when I'm at a 50% state of charge, I'm now slightly below 52 volts, right? So before I was up at 52.5, now I'm down below 52 for a C/5. As I increase the discharge rate, the curves shift downward. And if I'm at a C/2 discharge rate, I'm discharging very rapidly. I'm losing the most voltage across that resistor. And so typically it's on the order of a couple of volts. So I'll drop immediately from 54 down to 52 at a C/2 discharge rate. And at a 50% state of charge, I'm only about 51.4 volts, 51.3. So you notice that difference here. So just keep in mind that when you're looking at a voltage to determine the state of charge of a battery, it depends on how quickly that battery is charging or discharging. Daniel, I wanted to get into the temperatures. That was a good question that was asked earlier. The amount that the curve shifts down does depend on temperature. So what I'm showing you on the screen here is the resting voltages of individual LFP cells. These are not ours, but these are LFP cells that I had some students do some measurements on at our local university back when I was teaching there. And so these cells are shown, I'm showing you resting voltage for individual LFP cells. So it starts about 3.5 for fully charged, and it drops off depending on the state of charge. And then what I'm showing is I had the students hold the cells at constant temperatures in oil baths and run discharge cycles all at C/2. So fairly fast discharge cycle, but you can see how much the graphs shift down. The colder you are, the more of a downward shift you'll have for the curves. The good thing to note is in cold environments, as you discharge a battery, it won't stay at the same temperature. It'll rapidly heat up. And the internal resistance is greatest at low temperatures because you can imagine that electrolyte is pretty viscous the colder it gets. So hopefully I don't create confusion with this, but what this graph is showing you is that the amount that you shift down depends upon how quickly you're discharging a battery and what the internal temperature of the battery is. That's why I can't tell you that this is at room temperature. I can't tell you exactly what your discharge curve would look like because I don't know what temperature your batteries would be stored at. Great. If they're stored at room temperature, it looks something like this.
Yeah, that was a great answer. Thank you, Nathan. There's a couple other questions. I just want to make sure we're aware of everyone's time. We have about 11 minutes left. Drew is asking, is there any rebound with rest below 10%?
Absolutely. So what you'll see in a battery cycle is that the cells themselves, the lithium takes a while to kind of get into its best resting place, if I can say it that colloquially. So when you discharge a battery, let's suppose you discharge down to a cutoff of, let's say you go down to 48 volts, but you're in a discharge cycle to get there, right? You might hit 48 volts, and then as soon as your low battery cutout kicks in and you stop discharging your batteries, you'll see the battery cells rebound And typically, they'll rebound to what that resting voltage equivalent would be. So if you're in a discharge cycle and we hit down here at 40, let's suppose you set it at the recommended value of 50.1 that we give you, you'll hit that 50.1 somewhere around here, right? And it will, after the discharge stops, the voltage will bounce up probably to about 51, 51 and a half, something like that. When you hit 48, because you're on the knee, it'll bounce up much more. So yes, there is a rebound below 10% remaining charge life. Hopefully I answer that, Drew. I'm happy to answer it in more detail later, but I wanted to jump right into what Daniel was talking about. If you're going to be using the batteries in very low temperatures, these batteries can be stored in quite cold temperatures. We do just recommend that you try to run them through a charge cycle. Unlike lead acid batteries, the self-discharge rate of lithium batteries is very slow. Typically around 1% a month is the figure that engineering has given us, and they'll stay charged for a long time. Humidity is not often a huge consideration unless you live near the coast and you have a lot of salt water in the air. Then you might want to make sure that the batteries are protected from high levels of humidity that can come in with early morning fog from coastal communities. Cold temperatures definitely affect the charge cycle of all lithium batteries, and as long as we are using electrolyte batteries until we move to solid state batteries, it's a major consideration, right? You don't want to charge below freezing. So typically the lower limit of charge is 32 degrees Fahrenheit or 0 degrees Celsius freezing. I'll get to that in a second. I just want to point out that if you have your batteries enclosed inside some building, the typical internal temperature of the battery is not going to move as quickly as ambient temperature. When I'm saying you don't want to charge below freezing, I'm talking about the internal battery temperature. And because batteries generate heat when they're charging and discharging, the internal battery temperature is typically above ambient. One solution we have for this, we have these integrated heating pads. They can be wired directly into the BMS of the battery. If you're interested in this solution, we do have it, but it is a special order item. So if you're installing in cold environments and want heating pads to go under the battery to transfer that heat into the battery to keep them at optimal charging temperatures, these will turn on and turn off based on the internal battery temperature. So we can wire those into the batteries, give you that option. You also can use insulation in cabinets, especially in locations where you know it's going to be cold. You might throw one of these foam boards below the batteries to prevent that conduction of heat through the shelves, or use some of that foam insulation. So let me get to this slide that Daniel was asking about earlier, that somebody had asked about earlier, and Daniel was referring to. So for our non-communicating batteries, the PHI batteries, we're really limited in our temperature range to 0. We can't charge below 0, and that's because the lithium has a really hard time getting into the graphite. And so it can build up and even form what are known as dendrites or branches. It's basically solid lithium deposits that can damage the cells over time. So it's important, if you have non-communicating batteries, that you do something if you're in a cold environment to make sure that the charging equipment doesn't try to push charge in cold temperatures. For the communicating batteries with appropriate equipment, the communicating batteries can dictate how fast they want to be charged, and they monitor internal temperatures in various places within the battery cells. And so their charging range on these batteries can go all the way down to negative 20 degrees Celsius. And up to 50 degrees Celsius on the charge cycle. The reason that the line is kind of blurred here at the lower side is we slow down that charging rate in cold temperatures. So this slide here, if you want the details off of it, you'll all be getting copies of these slides today. This slide here indicates those temperatures. And so the charging range again is displayed here on the left. This is for communicating equipment with these the communicating batteries that have the more advanced BMS in them. The equipment is programmed to change the charging rate. So if we're in a cold environment, we have one of these AmpliPHI batteries with maybe a SolarArc or a SimpliPhi ESS, the new Briggs Stratton inverter. We can what will happen is when the batteries are cold, they can charge very slowly. So even at -20°C, we can charge at just an amp. That'll start to heat those batteries up. As they get warmer, we increase the charging rate to 3 amps. As they get warmer, we increase it to 20 amps. And that the charging process itself, you probably noticed from charging your phones in the past, like it heats the battery up, right? And so we can use the internal resistance of the battery to generate internal heat and heat the battery up as long as the ambient temperature doesn't go below -20 or the internal battery temperature stays above -20. And then as that battery gets hotter, we can actually charge that battery. I know the screen here said to 50°C, but we can charge that battery at a reduced rate, basically a C/5 rate at 15 amps, even in the 50 to 70°C range. So there's a lot of features to the more advanced BMS units in the SimpliPhi and AmpliPHI battery that you can take advantage of if you have temperature considerations to pay attention to. If we go above a 4 amp range, when we're in a low temperature conditions, so 0 to -20, the battery will protect itself by opening up the contactor. If we try to charge above 71°C, it'll cut off both on charge and discharge. And then there's a cutoff there for discharge at low temperature. If we're above 4 amps at -21, it'll cut off, and similar for the charge cycle. So these are the cold weather solutions that I was mentioning to you for these communicating batteries. So if that's of interest to you, let us know. I'm going to skip this example because I think I've only got 4 minutes left, Daniel.
Yeah, we got a couple good questions here I'm saving for the end for everyone.
Okay, so just want to let you know, it is important to size your systems appropriately. The batteries all have power ratings, right? In addition to storage capacity ratings, right? So a battery that's 75 amp hours, if we're discharging that over 2 hours, would be 37.5 amps per battery, right? And so that 37.5 amps times the nominal voltage tells us that each of these, the Phi and the AmpliPHI battery, can provide about 1.9 kilowatts each. So make sure to use the appropriate number of batteries for the equipment. So this is a 6 kilowatt unit. We get about 1.9 kilowatts for each battery, slightly undersized. But if you use communicating batteries, this would be okay. All right, so you can limit the equipment as well. Breakers, it's just important to note here, what's the point of this slide is to tell you that the breakers don't often trip rapidly. They trip slowly, and some of these breakers, you have to pay attention to the trip curves. And some of these breakers, you have to go above their rating in order to get them to trip at all. If you go, the higher you go above the rating, if I'm looking at 200% for the breaker on the left, it will trip in about 0.2 of a second, right? There's a log scale on the left. The breaker on the right, if I go at 200%, it would take 10 seconds for that breaker to trip. So if you're using breakers to try to protect your equipment, pay attention to the trip curves for those breakers. Here's a nice looking install shown with a couple of solarcs here. You can get, with communicating batteries, you can get a lot of information, and that gets communicated directly to the communicating equipment. So here's an interesting install. This install involves a load bank here because this particular customer has wind installed, or windmills installed to charge the batteries in addition to solar. On the right side here, you got 3 of these Boss 12 units. This is powering a school. I think this one, I'm not sure, but I think this one is in New York City. We did a number of libraries and installs there. I do want to point out one last thing in my closing couple of minutes. We have an elite installer program, and we've got a lot of participants installing our batteries worldwide. Our installer qualification program does give you cash back. We pay out $25 per battery, and that's stackable. You can get other rewards as well if we have other promotions running. So I know, for instance, if it's your first time installing a SimpliPhi system, there's a big rebate for installing your first SimpliPhi system. We've had $75 rebates for everybody, and you can stack this $25 on top of that if you're an elite installer. So if you're not an elite installer, consider joining our program. Send Daniel or I a message, and we'll help welcome you in. So that qualification program is on the left there. If you're interested in joining, you can either click on the slides once I send them to you, or use this QR code to access the application. So Daniel, you said there were a few good questions. Let's go ahead and take them. We're right at the top of the hour here, we're right in the middle of the hour here, and we're wrapping up. My email and Daniel's email is there on the screen, training@simpliphipower.com.
Yeah, if you're looking for your NABCEP credits, are you probably just going to say that? Sorry, Nathan. NABCEP credits, training@simpliphipower.com. Kennedy's asking, can putting cells in parallel be considered to be a cure for high internal resistance? Resistors in parallel have lower resistance. So how I'm thinking it is, why do the batteries have 3.2 volts? Why don't the battery cells have nominal 48 volts each, perhaps?
So nominal just means named voltage, right? And so yes, Kenny, as you put more batteries in parallel, that internal resistance decreases. But if you're discharging your system at a C/2 rate, you're going to pull twice as, let's suppose you double the number of batteries, but you pull double the amount of current. That internal resistance is still there. But yes, it does reduce. The more batteries you have, the lower the internal resistance goes. And keep in mind that we don't have 16 cells inside our 48-volt batteries. We have hundreds of cells. And so these are in stacks. I want to say 27 in parallel, and then 16 of those 27 cells in series. But I'm not certain on those numbers.
What are the advantages, disadvantages of LFP versus bidirectional charging with charging stations? So I think maybe Diane's asking about EV chargers.
I'm not certain I understand the question.
Email us.
But yeah, email us. And I will say this, these batteries are very efficient, and we can charge at very high round trip efficiencies. So for instance, let's suppose your car is not going to be parked at home, but you would like to capture solar energy during the day in the excess of the loads that your house has, and then save that extra energy and charge up your EV during the evening time. We're looking at a minimum of 92% round trip efficiency on our charge cycles. And the slower you go, the more efficient that gets. So we're typically looking at only 8% energy lost in this whole process. And with the MPPTs on the charge cycle, we can look at more like 98% efficiency on our charging. So you don't lose a lot of energy, and you can definitely take advantage of that. I'm not sure if I answered your question, because I'm not sure that I understood it correctly.
Thank you, Nathan, and thank you everyone for joining us.
Okay, any more questions, Daniel?
Oh, one just came in. I'm not sure what Drew is asking. Go ahead and email us, Drew, about your charge rate questions, and we'll end it there for everyone.
Okay, thank you, Daniel. I really appreciate it. And sorry for going a couple of minutes over, everyone. We always love the questions, and I'd love to stay on here. So feel free to call us, 805-640-6700, extension 3 if you're trying to reach training, or send us an email, training@SimpliPhi. The same if you're looking for those NABCEP credits. Go ahead and email us, training@SimpliPhi. Tell us how your name should appear on your NABCEP certificate. We'll check the attendance logs and get your certificates issued. Once again, everybody will get a copy of this training. The video link will be sent out, and the slides will go out to you. Thank you again. Bye.